thanks a lot for inviting me to come here. It's a big honor to be here. And I think it's nice to follow up on the previous talk, because I mentioned some of the same problems, but I will insist that we actually can learn something from fossil brain sizes. And as you already know, and if you didn't know in the morning, then you know by now, humans do have large and complex brains, even for a primate, right? So, and if we look at high resolution CT scans, computed tomographic scans of fossils like this Neanderthal fossil or a modern human fossil, then we can infer brain shape and brain size from the imprints that the brain leaves during infant development. So we can actually study the evolutionary changes of brain size, and in this schematic you see the familiar pattern that we have over the last few million years. Overall, a trend of a dramatic increase of brain size in the hominin lineage, right? So here we have chimpanzees, Pan, and here are two Australopithecus species, Homo erectus and Homo sapiens and Homo neanderthalensis, have really, really large brains. There are two notable exceptions to this overall trend, Homo floresiensis and Homo naledi. So especially with Homo floresiensis, it seems that this is not a one-way street. So it has been argued that in special conditions, if you're isolated on an island, then the brain size can also go down again. But of course, what we're really looking at, if we look at these plots, are changes in adult brain size, right, over time. So here I'm using chimpanzees as a stand-in for apes, but basically all apes and modern humans and Neanderthals, they bracket basically what has happened over the last few million years in our own lineage. And what we're really looking at is changes in brain development, right? Prenatal and postnatal brain development. And here, the reason why I'm plotting chimps and humans here is because that's where we have hundreds and hundreds, if not thousands of specimens. And so here I'm plotting endocranial volume against age. And you see that both chimpanzees and humans grow their brains and their endocranial volumes over time, but at very different speeds. One of the problems that we have with all of these data is that these are post-mortem data, right? So usually they come from skulls, or they're from post-mortem extraction of brains. So these people, the owners, the previous owners of these brains, they're dead, and they might have, they died for a reason, and that reason might have interfered with us being able to interpret properly healthy brain development. So it's comforting to see that if you do magnetic resonance imaging of healthy kids multiple times, so these lines are, at least 3 scans of the same individual over time, then you see that, healthy children, actually their growth curves, they overlap with what we find in the post-mortem data, which is good because that means that we can actually use this data to learn something about healthy development. So how can we now compare species like chimpanzees and humans that have such different adult values? Well, one way is to look at relative brain sizes and standardize these growth curves by the mean adult value, right? So I've set the mean adult value to 100% for both species, and then you see how the relative proportions of the brain change over time. And here you can see, and I think it's easier if I just show the adult values or the average growth curves. Here you see this typical contrast that we see between absolute endocranial volumes and relative endocranial volumes. We see in humans, we have this really rapid brain growth, but compared to chimpanzees, we actually grow more slowly, or we mature our brains more slowly. And that is something that is at least unique in living apes. So one of the questions we're interested in is how old is that pattern of brain growth? And there are a few species we can look or we can study this in. One is Neanderthals, because there's actually a decent sample of adult Neanderthals where we can make educated inferences about their brain size from these imprints. And so we've reconstructed using CT scans and virtual techniques. We've reconstructed Neanderthal babies and other Neanderthal kids. So, for example, this is a Neanderthal child from Mesmaiskaya, and you can assemble them on the computer and then compare these Neanderthal babies. There are two that are really nicely preserved, one from Mesmaiskaya, the other one is from Le Mostier in France. And what you see here, if you compare the Neanderthal baby with a modern human baby, is that some of the Neanderthal features, they are actually present at birth, right? Neanderthal babies already have bigger noses and taller orbits and overall a little bit larger face. But interestingly, both their endocranial shape, here the Neanderthal is in red and the blue is the modern human baby, is almost the same. So it's the shape and volume at the time of birth of the brain is basically identical or very similar in Neanderthals and modern humans. And that means that we can now plot, using all the other Neanderthal children that we reconstructed, we can plot the Neanderthal growth curve here, and we see how Neanderthals achieved a slightly larger average adult brain size than humans living today. Interestingly, if we plot the relative brain size, we see that the Neanderthal growth curve completely overlaps with the modern human one. So there is no, based on the data we have, there is no statistical difference between the modern human growth curve and the Neanderthal growth curve. And that includes, for those of you who follow the paleoanthropological literature very closely, a recent specimen from El Cidron in Spain. So these authors have recently argued that this 7.7-year-old Neanderthal actually is an indication for a longer period of brain growth in Neanderthals compared to modern humans, because it's smaller than the mean adult value. But that's actually not a very good argument, because nobody, like a single individual, is not expected to grow into the mean shape and average in the clinical. And there are actually adult Neanderthals that are smaller than the LC drone. So I think overall, right now we have to work based on a hypothesis that brain growth in terms of brain size is actually very similar in Neanderthals and modern humans. But that, of course, still means that their endocranial shapes, these differences between these elongated and these round globular shapes that we have in modern humans, might mean that there is a difference in brain organization, but at the same volume. So how far can we go back in time and trace this curve in our evolutionary lineage? So here, these are data from Homo erectus. So this is a species that it's for sure directly ancestral to both Homo sapiens and Neanderthals. And there's one infant or baby, actually, a Homo erectus baby, the so-called Mochocerto skull. And if you plot the absolute size of Mochocerto here, there are different, I would say, estimates of its endocranial volume, because it's not complete, but it's fairly complete. You see that it's actually completely outside the chimpanzee range, but would already fall into the Homo sapiens range. But the problem is that right now it's unclear what the relative brain volume of Mochocerto really is, because you can, depending on what you choose as your adult comparative sample, you get a really wide range, right? So Jean-Jacques and colleagues a few years ago basically emphasized that the Mocha-Kercho child is actually very chimpanzee-like in relative brain growth. But others have argued that if you use a different adult reference sample, because there are very small and very large Homo erectus adults, then, and if you compare it basically to very large Homo erectus adults, then it might be, human-like or chimpanzee-like. We don't know yet, right? And it's also inconclusive when we look at the relative brain size of Australopithecus africanus. So this is the famous town child that died between 2 and 3 years of age. And you see, in terms of absolute brain volume, it's actually very chimpanzee-like or ape-like. And in relative brain volume, it could be both growing according to a chimpanzee or human-like pattern, right? So at this point, we have to say we don't know how old that particular pattern of growing fast but maturing slowly really is. Not all hope is lost. There are other fossil species that might be interesting, but so far that's the evidence that's been published. And the textbook, I would say, model for explaining this, I would say, delayed and prolonged brain growth in Homo sapiens is related to the evolution of upright walking. And I think we'll hear more about that later in the afternoon from Hermann Ponzer. But basically the simple model is that a few million years ago, so between 4 and 6 million years ago, hominins evolved a peculiar way of locomotion. So they started to walk upright. And this upright walking changed the shape of the body, including the shape of the pelvis, right? So these are unnaturally stretched, but basically that's a gorilla as a stand-in for the shape and size of an ape pelvis compared to a modern human. And that is basically the reason here why it's so easy for a chimpanzee mother or any ape mother to give birth. If you Google chimpanzee birth, then there are a few YouTube videos, and I can show it to you, but I turned off my internet. But basically, it's a 21-second video, and the baby's out, right? So this would not be the case if you Google human birth, I guess. And the reason is that we give birth to babies that have heads that are as large as a chimpanzee adult, and B, our pelvis, the bony birth canal, is smaller, and presumably, and at least that's the idea, because we've evolved adaptations to upright walking. And here, this is how tight the fit is, so that a human baby has to rotate multiple times to fit through the birth canal, and this is an extremely risky process. So what we've done is we've basically delayed our brain growth, or large parts of our brain growth, outside of the mother's body. And at the time of birth, a human brain has 100 billion neurons, right? So that is an incredible number, and it's obviously not an exact number, but maybe to give you an idea how big that number is, so if you were to divide up that number over the 280 days of a normal pregnancy, then the developing baby grows 250,000 new neurons every minute, right? So if you have if somebody in the audience is pregnant, or you have a loved one at home who is pregnant, or you're a proud grandparent, then the time it took me to say this sentence, this baby grew 15,000 new neurons, which I think is very impressive. And this neuronal growth in the mother's womb is basically the explanation for this incredible growth of the brain in utero. And what's interesting here is that the chimpanzee brains, of course, also grow, but consistently throughout pregnancy, the chimpanzee brains are smaller than human brains, and already around week 22, the growth rate of chimpanzee brains starts to slow down. And there's no slowing down in humans, so this is a human fetus at week 22, and it just keeps growing until birth. And then after birth, humans keep on going at almost fetal rates and slow down very, very late. So humans grow faster than chimpanzees for a longer period of time. So in total, they mature more slowly. And that's just the number of neurons. We haven't even talked yet about the number of brain connections. So there are around 100 trillion connections that are being built, as Chris Kusawa just mentioned before. So when you're born, you have 100 billion neurons, but there are hardly any connections between them. So in the first years of life, we have this synaptogenesis, so all these connections are being built, this network. And then later on we have pruning. And maybe one additional comment to what was mentioned before. So one of the peaks in energetic costs, I think, is related to myelination. So there's not only new synapses that are being built and new connections, but they're also developing a myelin sheath, so the white matter develops, and that is a really, really costly process, and that peaks in these first years of life. And so some of the brain structures are actually, of these fiber tracts, of these white matter fiber tracts, are actually developed fairly early on, but they develop basically under the stimuli of the environment. So when you grow and how fast you grow actually affects the wiring pattern of the brain. So you might ask, okay, maybe obstetric constraints were important 2 million years ago, but why hasn't evolution fixed this by now, right? So why do we still have an obstetric dilemma today, even though we've been bipedal for quite some time? And I think one of the reasons is that there's a really strong selection and on birth weight of the child. So these are infant mortality charts of 1,000 live births. So this is a log scale, and here is birth weight in blue. And what this means is that if a live birth is around half a kilo only, then almost all the babies die, right, eventually. And the higher the birth weight, the better the infant survival, until it goes up again. So why does it go up again here when you have large babies? And that's one of the, I would say, puzzling things of human evolution. And colleagues from Vienna, Philipp and his group, they've recently published a model where they, I think, explain very convincingly why the obstetric dilemma is still around and why it's actually might be worse in the future, and I'll try to tell you why. So they've come up with what they call the cliff edge model, and it's a theoretical model where you have a variable d that explains the difference between the head of the baby and the birth canal of the mother. And because both the head of the baby and the matrix of the mother's pelvis have symmetrical distributions, also this difference between these two measurements has a symmetrical distribution, right? And the problem is that the individual fitness of the baby has a very unusual fitness curve. So you have an increase of fitness with more, with basically a larger baby, until the baby is too large for the birth canal, so there can be fatal complications. So selection basically pushes this curve very close to this cliff edge. And as a result, we actually have a number of babies where without medical intervention, without modern medical intervention, you have fatal complications for both mother and child, potentially. And the core of this fascinating mathematical model by Mitterker and colleagues is that the optimal fitness of the population, not of the individual, but of the population, includes individuals where you have fatal birth complications. So why doesn't evolution act on reducing that variance? Well, the answer is that this is really hard to do because mother and father both contribute to the gene pool of the baby, and mother and father don't evolve independently, right? So, and the selection on fatal birth complications only works on the female side of the genome, not on the male side of the genome. So basically, men aggravate the obstetrical problems in women. And what would happen if everyone was born using a C-section, right? If you remove that constraint, well, then you remove the cliff edge, and the prediction is that you actually have a 10 to 20% increase in cephalopelvic disproportion in modern humans within only 2 generations, right? So that is a very, very drastic evolution and a really quick change. So just to sum this up, so the selection for narrow pelvis may be related to bipedalism and or large brain leads to higher rate of birth complications. And as I mentioned, the genetic correlation between the 2 sexes aggravates the obstetrical dilemma, and cesarean sections therefore actively change human evolution. And what this group recently published is that this is not just a completely made-up fantasy theoretical model, but you can actually find these processes going on in actual data in living humans today. Okay, thanks a lot for your attention, and I'm happy to answer any questions you might have.